It's pretty wild to think that the same invisible force that lifts a 400-ton jumbo jet clean into the sky is the exact same force that glues a Formula One car to the track. It really just depends on which way you turn it. Air, the stuff we just walk through every day without a second thought, holds some of the most powerful secrets in all of engineering. Okay, let's get into it.
So to get us started, just take a look at these three things for a second. You've got a massive wind turbine, a high-tech race car, and a reusable rocket. I mean, on the surface, they couldn't be more different, right? But what's the invisible thread that ties them all together?
Well, the answer is that they are all absolute masters at manipulating the air around them. Every single one has been engineered with just breathtaking cleverness to harness an invisible force that governs how pretty much everything moves on our planet. And understanding that force? Well, that's what we're going to break down right now. We're going to pull back the curtain on this invisible connection by really digging into the fundamentals of aerodynamic forces. This is the science of how air and objects interact when they move past each other, and trust me, it is way more surprising than you might think. The basic idea here is actually super simple. Anytime an object moves through the air, or air rushes past an object that's standing still, forces are created. That's it. But from that one simple interaction, two very important and often opposing characters emerge. So let's meet our two main players in this whole story, lift and drag. Seriously, if you can get the basic difference between these two, you'll unlock the secret behind every single example we're about to look at. Okay, what's really important here is how simple this is. Think about sticking your hand out of a moving car window. You know that force that pushes your hand backward? That's drag. It's just resistance. But now angle your palm up just a little bit. Feel your hand get pushed up? That's lift. Now angle it down and it gets pushed down. That's also lift. It's any force that acts perpendicular at a 90-degree angle to the direction the air is flowing. All right, so keeping lift and drag in mind, let's check out how engineers have learned to harness the air in some really brilliant and kind of counterintuitive ways. This quote from a Formula One designer is just perfect. An airplane wing, right, is shaped to create lift, to pull the plane up against gravity. So what do you think happens if you take that exact same wing and you just flip it upside down? And this shows the result perfectly. A race car is basically a fighter jet that's trying to fly as close to the ground as possible. Its wings are upside down, generating what they call downforce, which is really just our friend lift, but acting in the downward direction. This force is so huge that, in theory, it could let the car drive upside down on a ceiling. On the track, what it actually does is smash the tires into the asphalt, giving them this insane level of grip and allowing for cornering speeds that just defy belief. The whole game for engineers is balancing that corner-winning downforce with the speed-killing drag it also creates. All right, next up, how does a wind turbine actually generate power? I think most of us assume it's like a giant pinwheel. The wind just pushes on the blades and spins them around. That would be using drag. But is that how these engineering marvels really work? The answer, and this is fascinating, is no. Wind turbines are actually incredibly sophisticated lift machines. The blades aren't just flat panels. They're shaped into what we call airfoils. That's just the fancy word for a wing shape, and they're designed specifically to generate lift. As wind flows over them, they create this powerful lift force that's perpendicular to the wind. Now, because of the precise angle of the blade, a tiny fraction of that huge lift force actually points forward, in the direction the blades are spinning. It's this small forward piece of the lift that overcomes the blade's own drag and drives the whole system. So they aren't pushed by the wind, they're literally pulled around by lift. So, from harnessing the wind here on Earth, our final example is going to take us all the way to the edge of space. You might think aerodynamics is just something a rocket has to fight against to escape the atmosphere, but for a modern reusable rocket, it's actually the key to coming home safely. And this is how they do it. As a Falcon 9 booster is falling back to Earth at supersonic speeds, these four things that look kind of like giant waffle irons deploy. They're called grid fins. Each one acts like a small steerable wing. By rotating them in the airflow, they generate a lift force. And by controlling the direction and the size of that lift from all four fins at once, they can steer that massive rocket booster with pinpoint accuracy all the way to the landing pad. It's like flying a skyscraper using four tiny little rudders. It's incredible. So in all these examples, the car, the turbine, the rocket, the one common ingredient that makes these forces so unbelievably powerful is speed. And that brings us to the most important question of all. What is the actual relationship between speed and aerodynamic force? Because it's not what you think, and it really governs everything. We all kind of get this intuitively, right? The faster you go, the stronger the wind feels on your face. But the way this force increases isn't intuitive at all. It's exponential. And understanding this one single rule explains so much about the world around us.
So here it is, the key to the whole thing, the v-squared rule. Aerodynamic forces scale with the square of velocity. This is why a nice, gentle 10-mile-per-hour breeze feels pleasant, but a 100-mile-per-hour hurricane, which is only 10 times the speed, has 100 times the destructive force and can flatten buildings. It's why when you double your car's speed from 30 to 60, the fuel you burn just to fight the wind doesn't just double, it quadruples. This rule is an absolute powerhouse.
But why does this happen, right? Why is it v squared and not just v? The logic behind it is actually incredibly simple and kind of beautiful when you break it down into two parts. Okay, here's how it works. First, the faster you go, the more air molecules you slam into every single second. So the amount of air you're moving is proportional to your velocity. That's 1v. Second, the faster you're going, the harder you have to shove those molecules to get them out of your way. So how much you accelerate them is also proportional to your velocity. That's the second v. So you're hitting more air and you're hitting all of it harder. You multiply those two effects together and you get a force that's proportional to velocity times velocity, v squared. And that simple rule, it's everything in aerodynamics. It dictates why a 747 needs such enormous wings and insanely powerful engines to even get off the ground. It explains why a Formula One car, even with over 1,000 horsepower, eventually hits a wall of air resistance on a long straightaway that its engine just can't overcome. It is the fundamental law that every aerodynamic engineer is either battling against or trying to harness every single day. So now you know the secret. The next time you see a flock of birds flying in that V formation, or watch a cyclist tuck down low, or even just feel the force on your hand outside a car window, you'll see it. You'll understand that invisible push of lift, the constant pull of drag, and the awesome exponential power of the v-squared rule. The only question is, where are you going to see it at work next?